Lesson 5, Induced Potential. This lesson is looking at generating electricity. It is the opposite effect of the motor effect, and it is called the generator effect. The generator effect is basically when a wire is moved between the poles of a magnet, a current is induced across the ends of the wire, and if that wire is in a loop, it creates a circuit, and therefore it will create a current in that circuit, as we can see here. So here we've got two poles of a magnet, a wire held below the magnetic field. Watch what happens when the wire is moved in the magnetic field.
If we move the wire up through the magnetic field like this, then a potential difference is induced across the ends of the wire. However, when the wire stops moving, then the potential difference is lost.
Okay, so all that has to happen is a wire has to move across a magnetic field, and the potential difference is generated across that wire. Okay, and that is the generator effect. So the induced current generates a magnetic field which opposes the original change. In other words, the current basically goes to try and stop the movement. Okay, all you need to really effectively know is that moving a wire in between the poles of a magnet, a current is induced in that wire. This is described using Fleming's right-hand rule. Again, this time it is right hand rather than the left hand. The fingers are held at right angles as before with the left-hand rule. All fingers indicate the same things. Current is indicated by the second finger. First finger indicates the magnetic field, north to south, and the thumb then indicates the direction in which the motion is of the wire. Okay. However, it doesn't actually matter whether it's the wire that is moving or the magnetic field that is changing direction. As long as there is relative movement between a wire and a magnetic field, current is induced. So we can see that if we look at this example, we have a coil of wire or solenoid connected to, in this case, it's a sensitive ammeter. That's microamps there. And all that's going to happen is you will see a magnet up the right of the screen here coming in, and watch what happens the needle on the meter as the magnet moves. The key thing here is watching the magnet moving. When the magnet is stationary, there is no effect. So magnet comes in, needle moves to the left, magnet out, needle moves to the right. Magnet in, needle to the left, magnet out faster this time, goes a bit further. Watching the magnet is stationary, no current. Magnet comes out, less current, went up to 10 that time, goes in slowly to 10, goes out fast, went to 20. So the speed at which the magnet moves also dictates the size of that current. Go away. Okay, sorry about that. So what we've got here is increasing the strength of the magnetic field, like we've seen with the electromagnetism. Increasing the strength of the magnetic field will increase the induced potential or increase the current. Moving the wire faster increases the current. Using a longer wire, which is basically using a coil of wire, so the bigger the coil, the more current can be induced as well. Key rules then: when the magnet moves into the coil of wire, a current is induced, so there has to be that movement. When the magnet stops, the current stops. That is key. So if there's no movement between the wire and the magnet, there is no current induced. When the magnet is moved out of the wire, the current is induced, but in the opposite direction. So if you move the magnet in, as we saw in the video clip, current goes one way. Move it out, current goes the other way, which is the reason why we actually generate alternating current in our power stations. Okay, so Fleming's right-hand rule used to describe the induced currents. Thank you.